1963. New Zealand mathematician Roy Kerr solves one of Einstein's most difficult equations. Rotating black holes. Not the idealized, non-spinning kind. Real black holes. The ones that actually exist. Stephen Hawking, 32 years old, refines the theory. He predicts exactly what happens when two rotating black holes collide. The gravitational waves they'd emit. The frequency of the final ringdown, down to mathematical precision. The problem? No technology exists to test it. So physicists wait. Decades pass, generations of scientists. LIGO gets funding, gets built, gets upgraded. September 14th, 2015. First gravitational wave detected. Hawking celebrates. The wait seems over. March 14th, 2018. Stephen Hawking dies. January 14th, 2025. LIGO detects GW250114, a black hole merger so precise, so clean, that for the first time, scientists can test Hawking's most specific predictions. The ringdown, the quasinormal modes, the area theorem. All match. Perfectly. Hawking was right. To 12 decimal places. 7 years too late for him to know. Roy Kerr wasn't looking for fame. He was solving a problem. Einstein's field equations describe gravity as curved spacetime, but they're notoriously difficult to solve for specific situations. 1916. Carl Schwarzschild found the first solution. A non-rotating, perfectly spherical black hole. Beautiful, elegant, unrealistic. Real black holes form from collapsing stars. Stars rotate. Angular momentum is conserved, so black holes rotate. Fast. 1963. Roy Kerr, at a conference in Texas, presents his solution. The metric for a rotating black hole. Not just any rotation. The mathematics describe how space-time warps around a spinning black hole. The frame-dragging effect. Space-time itself rotates. The ergosphere, region where nothing can stand still. Event horizon shape. Oblate, not perfectly spherical. The room goes silent, then erupts. This is it. The real geometry of black holes. But it's just math. Beautiful math, with no way to test it. Stephen Hawking was 32 when he made his most famous prediction. Not Hawking radiation, that came later. This was about black hole collisions. If two rotating black holes spiral into each other, what happens? 3 phases. In spiral, the black holes orbit closer and closer, speeding up, emitting gravitational waves that carry away energy and angular momentum. Merger. They collide. Space-time violently warps. The geometry becomes chaotic. Ringdown. The combined black hole settles down, rings like a struck bell, emitting gravitational waves at specific frequencies as it stabilizes into a simple Kerr black hole. Hawking proved something remarkable about that final black hole. The area theorem. No matter how much energy radiates away as gravitational waves, the surface area of the final black hole must be greater than or equal to the combined surface areas of the original two. Surface area can never decrease, and he calculated the ringdown frequencies. Quasinormal modes. The specific pitches the black hole would sing as it settled. These frequencies depend only on the final black hole's mass and spin. Nothing else. Hawking wrote down exact predictions, equations, numbers, and then nothing. No way to check. For decades.
Why are gravitational waves so hard to detect? Imagine two black holes, each 30 times the mass of the Sun, colliding a billion light-years away. The gravitational waves reach Earth. How much do they stretch and compress space-time? LIGO's arms are 4 kilometers long. The gravitational wave stretches and shrinks that distance by 1/10,000th the width of a proton. A proton is 10 to the power of -15 meters. The distortion is 10 to the power of -19 meters. Analogy. If the distance from Earth to the nearest star, 4.2 light-years, were a LIGO arm, the gravitational wave would change that distance by the width of a human hair. And you need to measure that. While Earth is shaking from traffic, earthquakes, ocean waves, thermal fluctuations. 1970s to 1980s. Most physicists thought this was impossible, but a few believed, and they started building. The first attempt, Joseph Weber, University of Maryland, 1960s. His detector, an aluminum cylinder, 2 meters long, 1 meter thick, a resonant bar. Theory. Gravitational waves would vibrate the bar at specific frequencies. Sensitive instruments would detect the vibration. 1969. Weber announced detection. Initial excitement. Then other groups built similar detectors, found nothing. Weber's results. Either false positives or instrumental artifacts. But he proved the attempt was worth making. 1970s to 1980s. Rainer Weiss, MIT, and Kip Thorne, Caltech, develop a better concept. Not resonant bars, laser interferometry. The idea: 2 perpendicular arms, 4 kilometers long. Laser beams bounce between mirrors. Gravitational waves stretch one arm, compress the other. The laser interference pattern shifts. 1980s to 1990s. Funding battles. Congressional skepticism. You want $300 million to detect something that might not exist. 1994. National Science Foundation approves funding. Construction begins. 2 sites. Hanford, Washington, Livingston, Louisiana. 4-kilometer arms, vacuum tubes, laser systems. Mirrors suspended by sophisticated isolation systems. 2002. Initial LIGO operational. 6 years of observations. No detections. Not sensitive enough yet. But they were getting closer. 2010 to 2015. Major upgrades. Advanced LIGO. New lasers. Better mirrors. Improved seismic isolation. More sophisticated noise reduction. Sensitivity increased tenfold. Could now detect events from 10 times farther away. Volume surveyed, 1,000 times larger. September 14th, 2015. 4:50 a.m. Central Time. Advanced LIGO had been online for 2 days. Still in engineering mode. Not officially observing yet. Both detectors, Livingston and Hanford, see the same signal. A chirp, starting low, rising in pitch, then cutting off. First thought, is this a test? Did someone inject a fake signal? No, it's real. They match it to theoretical predictions. 2 black holes, 36 and 29 solar masses, spiraling together. Merger occurred 1.3 billion light-years away. The signal includes the Ringdown, but it's faint.
Low signal-to-noise ratio, SNR of 26. They can confirm gravitational waves exist, can extract black hole masses, but can't test the fine details of the Ringdown. Can't check Hawking's specific predictions. Not yet. For that, they needed a louder signal. February 11th, 2016. The announcement. LIGO detected gravitational waves. Einstein was right. Black hole mergers confirmed. Stephen Hawking's reaction. This discovery is the first detection of a black hole binary system and the first observation of black holes merging. He'd waited 42 years, since his 1974 predictions. Gravitational waves, confirmed. Black holes, confirmed. But his specific predictions about the Ringdown? Not tested yet. Signal not clean enough. 2016 to 2018, more detections. Dozens. Each one teaching something new. But none with high enough signal-to-noise ratio to precisely test quasinormal modes or the area theorem. March 14th, 2018. Stephen Hawking dies. Age 76. Tributes pour in. One of history's greatest minds. But he never saw the precision tests of his predictions. The universe hadn't finished speaking yet. After Hawking's death, the search continued. LIGO now works with partners. Virgo in Italy, KAGRA in Japan. A global network. Third observing run, 2019 to 2020. Dozens of detections. Signal quality improving, but still not quite there. 2020 to 2023. Pandemic shutdown. But researchers used the time for upgrades. Better lasers, better optics, better algorithms for extracting signals from noise. May 24th, 2023. Fourth observing run begins. The detectors are now so sensitive, they detect one black hole merger per week. Sometimes more. By late 2024, over 300 black hole mergers detected. Each one tests general relativity. Each one narrows the parameter space for alternative theories. But researchers are looking for something specific. A signal loud enough and clean enough to test the Ringdown in detail. High signal-to-noise ratio, preferably with rapidly spinning black holes, where Kerr effects are strongest. They don't have to wait long. October 11th, 2024. GW241011. A black hole merger 700 million light-years away. Two black holes, 17 and 7 solar masses. The larger black hole, one of the fastest spinning ever detected, near the theoretical maximum allowed by general relativity. Signal-to-noise ratio, very high. One of the loudest signals ever, clean enough to extract details. For the first time, researchers can compare the Ringdown to Roy Kerr's predictions with high precision. Result? Perfect agreement. The rapidly spinning black hole leaves its fingerprint in the gravitational waves, exactly as Kerr's mathematics predicted 61 years earlier. November 10th, 2024. 1 month later. GW241110. 2.4 billion light-years away. Black holes. 16 and 8 solar masses. Something unusual. The primary black hole spins opposite to its orbit, counter-rotating, never seen before in gravitational waves. Both GW241011 and GW241110 show something fascinating. These might be second-generation black holes. Black holes that formed from earlier mergers, merged again. Hierarchical mergers. But the truly historic signal was still to come.
January 14th, 2025. Both LIGO detectors operating. Virgo and Cagra offline for maintenance. A signal appears. GW250114. Immediately, researchers know this is special. Signal-to-noise ratio, 80. The highest ever. 3 times higher than GW150914, the first detection. All 3 phases visible with exceptional clarity. In spiral, clean, loud. Merger, detailed. Ringdown. For the first time, crystal clear. Not just the fundamental ringdown frequency, the overtones too, like harmonics in music. Multiple quasi-normal modes extracted. The realization. This is the signal they've been waiting for. Clean enough to test Hawking's area theorem. Precise enough to measure quasi-normal modes to unprecedented accuracy. After 51 years, the universe finally provided the data. January to March 2025. Teams worldwide analyze GW250114. First, extract basic parameters. Masses of initial black holes, approximately 35 and 30 solar masses. Distance, about 1.8 billion light-years. Final black hole, 62 solar masses. 3 solar masses radiated as gravitational wave energy. Spin of final black hole, moderate, about 0.69, where 0 equals not spinning, 1 equals maximum spin allowed. Then, focus on the ringdown. Isolate the final milliseconds after merger. When the perturbed black hole rings as it settles into a stable Kerr geometry. Extract quasi-normal mode frequencies. Fundamental mode, 250 Hz. The pitch of the black hole's ringing. First overtone, 500 Hz, octave above fundamental. Second overtone, 750 Hz, barely detectable but present. And their decay rates, how quickly each tone fades. These depend only on the black hole's mass and spin. Compare to Kerr's predictions, the equations written in 1963. The match is perfect. Now the crucial test, Hawking's area theorem. Before merger, black hole 1, 35 solar masses. Event horizon area A1. Black hole 2, 30 solar masses. Event horizon area A2. Combined area A1 plus A2. After merger, final black hole, 62 solar masses. Spin 0.69. Event horizon area A. Final. Hawking's area theorem states A final greater than or equal to A1 plus A2. The final area must be greater than or equal to the sum of the initial areas. Calculation using GW250114 data. Initial combined area, 1.56 times 10 to the power of 10 square kilometers. Final area, 1.63 times 10 to the power of 10 square kilometers. A, final, greater than A1 plus A2. Check. The theorem holds. But more than that, the precision. Uncertainty in measurement.
plus or minus 0.3%. The theorem isn't just confirmed, it's confirmed to 3 decimal places. Bonus: the no-hair theorem also validated. Black holes are defined by only 3 properties: mass, spin, charge. Nothing else. The ringdown depends only on mass and spin. As predicted, no deviations, no extra hair. General relativity passes its most extreme test yet. April 2025. The LIGO-Virgo-Cagra collaboration announces results. Multiple papers, technical details, statistical analysis. Headlines: GW250114 confirms Hawking's black hole area theorem. Most precise test of general relativity in extreme gravity. Black hole ringdown matches Kerr predictions perfectly. Reactions from physicists worldwide. This is the confirmation we've been waiting for since 1974. Hawking would have loved to see this. General relativity continues to pass every test we throw at it. Importantly, no deviations from general relativity detected. Alternative theories of gravity? Ruled out with higher confidence. Extra dimensions? No evidence. Modified gravity? No support. Einstein's theory, combined with Kerr's solution and Hawking's theorems, describes black hole mergers perfectly. After 51 years, the universe kept its appointment. March 14th, 2018. Stephen Hawking died. He was 76. Had lived 55 years beyond his initial diagnosis. A medical miracle in itself. His final years, he celebrated the first gravitational wave detection, saw dozens more, knew his predictions would eventually be tested, but didn't live to see the precision test. GW250114 came 7 years too late. His 1974 predictions, written by hand, refined over years, published in technical journals, now experimentally confirmed to 3 decimal places. He's not alone in history. Einstein died in 1955. Didn't see gravitational waves detected, 2015. Chandrasekhar predicted black hole masses. Died 1995, decades before LIGO confirmed them. Oppenheimer predicted neutron stars. Died 1967, before pulsars discovered. Fundamental physics moves slowly. Predictions can take decades to test. Sometimes the theorist doesn't live to see vindication. But the work endures. The equations persist. The predictions wait for technology to catch up. And sometimes, the universe cooperates. Roy Kerr is still alive, 90 years old, lives in New Zealand. 1963, he solved the rotating black hole equations, age 28. 2025, his solution confirmed by the universe's most violent events, age 90. He's seen it all. The first detection in 2015, the Nobel Prize to LIGO founders in 2017, hundreds of detections since, and now GW250114, the definitive test. His metric describes every rotating black hole in the universe. Every merger LIGO detects uses Kerr's mathematics to interpret the signal. Every ringdown frequency is calculated using Kerr's equations. 2023, Kerr received the Crafoord Prize, often called the Nobel Prize of Astronomy. 2016, Royal Society's Hughes Medal. 2013, Albert Einstein Medal. Recognition came late, but it came. And unlike Hawking, he lived to see the full experimental confirmation. The universe's most violent events vindicated a 28-year-old's mathematics. GW 250114 isn't the end. It's a milestone. LIGO is upgrading again. A+ configuration, even better sensitivity. Expected operational late 2020s. Europe is building Einstein telescope, underground, 10 times more sensitive than current LIGO. 2030s. USA planning Cosmic Explorer, 40-kilometer arms, 10 times longer than LIGO, even more sensitive. 2030s to 2040s, and in space. LISA, Laser Interferometer Space Antenna, launching 2030. Will detect supermassive black hole mergers. What will these detect? Thousands of black hole mergers per year, more precise tests. Edge cases where general relativity might break down. The ultimate goal: find where general relativity fails. Einstein's theory describes gravity classically, but at the quantum level, we don't know how gravity works. Quantum gravity remains unsolved. Black hole mergers are laboratories, the most extreme gravitational fields in the universe. If general relativity breaks down anywhere, it's there. So far, no breakdown. GR keeps winning. But scientists keep looking. Because when we find the limits, that's when new physics begins. And the universe keeps providing test cases. (1974). Stephen Hawking, 32 years old, writes down predictions. Black holes have area. That area cannot decrease. When they merge, specific frequencies emerge. 51 years pass. Technology advances. Computers get faster. Lasers get more precise. Engineers solve impossible problems. LIGO gets built, gets upgraded, gets refined. First detection, 2015. Hawking celebrates. Vindication begins. But precision tests require better data, and Hawking runs out of time. January 2025. GW 250114. Signal-to-noise ratio, 80. Perfect clarity. Area theorem, confirmed. Quasinormal modes, match perfectly. No-hair theorem, validated. Everything Hawking predicted, correct. There's something profound about predictions that outlive their creators. The equations don't care if you're alive to see them confirmed. They wait, patient, carved into the structure of reality. Eventually, technology catches up. Engineers build the instruments. Experimentalists collect the data. And the universe speaks. When theory and observation align perfectly, across 51 years, across 1.8 billion light-years, down to 3 decimal places. That's not coincidence. That's understanding reality. Hawking never saw it, but his mathematics did. Kerr saw it, after 62 years. The LIGO team made it possible. Thousands of engineers, scientists, technicians. And the search continues. More signals coming. More tests waiting. The universe kept its appointment. 7 years late for Hawking to know, but right on time for his legacy to be confirmed. This is Cosmic Canvas, where we celebrate science's patient victories, even when the heroes don't live to see them. Until next time, trust the math and give it time.